You know, every once in a while, a new material comes along that just promises to change, well, everything. Today, we're going to dive into the story of metal-halide perovskites, a type of crystal that's gone from a lab curiosity to a real contender for our tech future in like a little over a decade.
So let's just start with a number, 27%. Now, you might be wondering, what's so special about that? Well, that is the record power conversion efficiency for a single perovskite solar cell. I mean, to give you some context, it's right on the heels of commercial silicon, a technology that's had decades and decades to get where it is. This is what all the buzz is about.
But honestly, this story is so much bigger than just solar power. Metal-halide perovskites are basically a whole new platform for a huge spectrum of technologies. We're talking everything from the LEDs in our screens to advanced sensors and even all the way to the building blocks of quantum computers. So what exactly is this wonder material? Where did it even come from? And what gives it all these incredible abilities? To really understand its future, we've got to go back to the beginning. We've got to look at its fundamental blueprint. Here's the first thing you need to know. The word perovskite doesn't refer to one specific chemical. Nope. It's actually the name for a very specific crystal structure. The original was a mineral called calcium titanate, found way back in 1839. But that first discovery, it was a metal oxide, and it's definitely not the material that's causing all this excitement today. At the heart of it all is its crystal structure, which we call ABX₃. Think of it like a set of really simple repeating building blocks, kind of like atomic Legos. You have a big atom at the corners, a smaller one right in the center, and other atoms on the faces. They all link up to create this really powerful 3D network. And that simple, elegant structure? That's the secret to all its amazing electronic properties. And this right here is the crucial point. Those original oxide perovskites, yeah, they weren't great semiconductors. But the modern metal halide perovskites we're talking about today, whoa, it's a completely different story. They absorb light like crazy and have what scientists call a tunable band gap, which just means you can tweak their recipe to absorb specific colors of light. This makes them absolute semiconductor superstars. So where did this superstar material first make its name? In the world of solar power. And what it's done there? It's been nothing short of revolutionary. I mean, just look at this chart. In 2009, the very first perovskite solar cell came in at a measly 3.8% efficiency. In just 15 years, that number has skyrocketed past 26%. Think about that for a second. It's done in 15 years what its main competitor took like 50 years to achieve. That is the fastest rate of improvement for any solar technology in history, period. Okay, so how do they actually do it? How do they turn sunlight into electricity so effectively? What's the secret sauce inside that thin, dark film? Well, the process is actually surprisingly straightforward. It all boils down to 4 key steps. First, the perovskite layer soaks up sunlight, which gets electrons all excited and creates these things called electron-hole pairs. Second, a tiny electric field inside the material splits those pairs apart into free charges. Third, those charges get whisked away in opposite directions through special layers. And finally, electrodes at the top and bottom collect those charges, and boom, you've got electricity. Absorb, separate, transport, collect. Simple as that. And this diagram here gives you a perfect picture of that process. A solar cell is really just a fancy sandwich. The perovskite layer is the really important filling in the middle. It's tucked between an electron transport layer and a hole transport layer. This whole structure basically acts like a one-way street, making sure those charges get out of the device efficiently before they can waste their energy. Now, besides just raw efficiency, perovskites have another massive advantage: how you make them. To make silicon, you need insanely high temperatures and a ton of energy to create those pure, rigid wafers. Perovskites, though, you can make them using low-temperature methods, almost like you're printing with an ink. This completely opens the door for cheap, lightweight, and even flexible solar cells. But like we hinted at in the beginning, this revolution doesn't stop with solar panels. The very same magic that makes perovskites amazing at capturing light also makes them fantastic at emitting light and detecting it. So let's go back to that application wheel. We've talked a lot about solar cells, but now we're going to explore some of these other incredible possibilities that are being cooked up in labs all over the world right now. And this list is, well, it's just breathtaking. We're talking about super pure, highly efficient LEDs that could make our TV and phone screens way more vibrant and use less power. In medicine, their ability to see high-energy particles could lead to incredibly sensitive, lower-dose X-ray machines. And get this, They could even be the foundation for new types of computer memory, advanced lasers, and even parts for quantum computers. The versatility is just astounding. All right, I know what you're probably thinking. This all sounds incredible, maybe a little too good to be true. So what's the catch? Let's talk about the real-world challenges that scientists are working on right now to get perovskites ready for prime time. It's the big question, isn't it? With all this amazing promise, why isn't your phone already being powered by a perovskite solar cell? Why aren't all of our TVs using perovskite LEDs? Well, there are two major hurdles that are still standing in the way. The two biggest issues are instability and toxicity. Early perovskites would break down pretty quickly when they were exposed to moisture or even just light. On top of that, the best performing recipes right now contain lead, which, raises some environmental concerns. But, and this is a big but, for each of these problems, scientists are developing some really clever solutions. For stability, they're creating better ways to seal the material off from the environment. And to deal with the toxicity, they're busy designing new lead-free options and smart recycling plans. But even with these challenges, the feeling in the scientific community is pretty clear. As this quote from a recent paper puts it, metal-halide perovskites are seen as a pivotal class of promising candidates. The potential is just too massive to ignore, and the speed at which they're solving these problems has been truly remarkable. So, we're left with this huge question. From solar energy and dazzling displays to medical imaging and quantum computing, this one crystal structure has the potential to totally redefine a whole bunch of industries. The road to the mass market still has some bumps, for sure, but if they can be overcome, we may very well be looking at the material that helps build the 21st century.